Hi, my name is Moonhun Park. I work at King Mongkut's Institute of Technology, Lat Krabang, in short KMITL, which is located in Bangkok, Thailand. And today I'd like to talk about a simple model that can explain the coupling between circular membrane and Helmholtz resonator. We all know what the Helmholtz resonator is. Basically, it is a cavity of some volume with a port through which the air inside and outside of the enclosure can interact. It is a very simple structure that is used in many applications in acoustics. For example, it is an excellent model of various acoustic systems, including microphone capsules, loudspeaker cabinets, and musical instruments, especially almost all string instruments. And also, it is an essential component of many acoustic liners and absorbers, and some acoustic metamaterials and energy harvesters. The Helmholtz resonator is usually modeled as a mass spring system, and we assume that the air in the port behaves as a mass, which is under the influence of the restoring force acted by the air in the cavity. Then it is well known that the structure will resonate at a single frequency, which is related to the speed of sound c, the surface area of the port, the cavity volume V0, and the port length Lp. This formula is quite useful in many cases, but in many other cases, it fails to give us good estimates of the actual resonance frequency. Some of those cases are when the surface of the enclosure is flexible, readily responding to the pressure change in and out of the cavity, in which case we may not use the well-known formula. In the past, there were some successful models that could explain the resonance characteristics of the Helmholtz resonator with flexible surface. For example, a 2-degree of freedom lumped element model was set up where the flexible surface was assumed to be the second mass. In a more sophisticated model, a thin plate was considered for the flexible surface, which must satisfy the Kirchhoff-Love plate equation. In another category of models, the flexible surface was considered to behave as a fully flexural circular membrane, but with a negligible port length, which means that there is no mass in the port to interact. In this presentation, I'd like to talk about a simple model of Helmholtz resonator coupled with a fully flexural circular membrane. Here is an illustration showing the circular membrane of radius AD and its displacement XD as a function of r, theta, and time t. And the air in the port, we assume that it behaves as a mass mp and its displacement is xp. Then we can set up 3 equations. First, we need the wave equation for the membrane displacement xd, and the second is the equation of motion for xp. These 2 displacements, xd and xp, are under the influence of the pressure change delta p in the cavity. And we can represent this delta p by using many known parameters, including the net displacement of the membrane. By using the third equation for delta p, we can combine the first and the second equations and decouple xd from xp. And solving the decoupled wave equation, we arrive at a conditioning equation, which is shown here on the next slide. In this conditioning equation, we have 2 Bessel functions, the 0th order and the 2nd order. And the constant b is the substitute for a combination of many parameters regarding the membrane port and the cavity, where capital T is the membrane tension. ZH contains the resonance frequency of the normal hardware Helmholtz resonator. And finally, z is the variable of the equation, where we also have the wave speed cd on the membrane. If we solve this equation numerically for z, we can determine the resonance frequencies of the membrane-coupled Helmholtz resonator. But I need to tell you that this conditioning equation is valid only for the 0 n mode, which has no nodal lines across the membrane. Before I start talking about the solutions of this conditioning equation, I would like to go through some limiting cases of the parameters used in the equation. For example, if we consider the volume to be very big, V0 infinity, then the constant B will become 0, which will make the right-hand side of the equation 0. When V0 goes to infinity, the Helmholtz resonance frequency omega h will also go to 0, and so the equation is reduced to that of the membrane-only case. If we assume that the membrane becomes very small with AD approaches 0, or the membrane tension becomes so high, the constant B will also be 0, in which case we can show that the only solution of this conditioning equation is Z equals ZH, which means that the system will behave as the normal hardware Helmholtz resonator. Now, if B is not 0 anymore, but ZH is equal to 0, then we are talking about the membrane fitted to an airtight cavity. And the equation is reduced to that for the cattle drum, which you can find in Kinsler's well-known textbook, Fundamentals of Acoustics. Finally, if both B and ZH are not 0, solving the equation will give us the resonance frequencies of the membrane-coupled Helmholtz resonator. So it looks like this conditioning equation is valid not only for the membrane-coupled Helmholtz resonator, but for the 4 related systems as listed in this table. To find the solutions for the equation, we could simply put it in the computer to get some numbers back. But if we rearrange the equation, isolating ZH on the left-hand side from everything else, including the variable Z on the right-hand side, we might be able to better understand how changing parameters would modulate the resonance frequencies. So the right-hand side of this rearranged equation, we're going to define it as capital H. And if you plot H, for example, for the constant B equal to 50, then we'll have these blue lines. Then the value of ZH can be indicated as a horizontal line in the same graph, and the roots of the equation can be found where the blue lines meet the green horizontal line. And we're going to call these values as ZC1 for the first mode, ZC2 for the second mode, and so on. And finally, we can retrieve the nth mode resonance frequency from the ZC values. If the dimensions of the cavity or the port happen to change, then the new ZH value must be used, and the resonance frequencies will also change accordingly. Seeing how the function h changes with the value of the constant b is more interesting. I'm now making b smaller all the way down to 1. And if we consider the limiting case of b approaching 0, h will be equal to z, becoming the identity function. Given this trend of the function hz, we can easily see that as we make the value b smaller, the lowest resonance frequency will increase, but those corresponding to the higher modes will decrease. We can also see that the function h is 0 or goes to infinity which happens when Z is equal to the roots of the zeroth and second order Bessel functions. Now that we have the solutions of the equation ready, which are basically the predicted resonance frequencies of the system, we'd like to validate the model in the measurement. So for the measurement, we mounted an 8-inch drum head as membrane to a solid heavy frame, and on top of it, we placed a custom-made drum hoop. With this drum hoop, we can fix the drum head to the frame and also adjust the surface tension of the membrane. And this will be the membrane-only setup for the measurement. On top of the membrane-only setup, we mount an enclosure with an opening of 4 cm diameter and completely seal the opening with a lid. Then this will be the setup for the kettle drum, which is basically a circular membrane fitted to an airtight cavity. If we now replace the lid by a short pipe, then we have a setup for the membrane-coupled Helmholtz resonator with a port length of 4 cm. So we measure the frequency responses of these 3 systems, where the first cavity volume was 500 milliliter for the kettle drum and MCH, but we also measured for a bigger cavity of 800 milliliter. With one of these systems mounted to the frame, a shaker was driving the membrane at the center, exciting the zero end modes mostly. And the input force was measured by a sensor. The velocity on the membrane was recorded by a laser vibrometer, and the sound produced by the membrane was also recorded by a free-field microphone. And all these sensor signals were captured by a dedicated interface which was controlled on the PC. In this presentation, I'm not going to talk about the laser signals, but I'll be sharing with you the acoustic responses of the systems, which are the microphone signal divided by the force sensor signal in the frequency domain. So here is the acoustic response for the membrane-only case. There are 4 prominent resonance peaks as indicated by the blue downward arrows. Next to those, you can also see the red arrows indicating those predicted by the classic model, which you can find in the Kinsler's textbook. These are the resonance peaks corresponding to the zero end modes without the straight nodal lines through the membrane center. The difference between the prediction and the measurement in terms of the resonance frequency in hertz is also indicated on the bottom of the slide. On this slide, we have acoustic responses determined for the kettle drum case. The solid line is for the smaller cavity, and the dashed line is for the larger one of 800 milliliter. Compared to the membrane-only case, you can see that the resonance frequencies are now higher, and the extent of the upward shift is more prominent with the smaller volume compared to the larger one. Here also, the resonance frequencies predicted by the Kinsler's model are indicated, which are different from the measured values by some tens of hertz. And these are the results for the membrane-coupled Helmholtz resonator. And you can see that compared to the kettle drum case, the resonance frequencies are shifted even higher, which is more prominent for the first 2 modes, where the extent of the shift is not very clear for the resonance frequencies above 1000 Hz. And as predicted by the proposed model, an additional resonance peak appears at very low frequencies, which are actually even lower than the resonance frequencies of the corresponding hardware Helmholtz resonator. And the accuracy of the proposed model seems to be comparable to the Kinsler's models, which were valid only for the kettle drum and the membrane-only case. So here is a summary of my talk. First, I propose a simple model which could estimate the resonance frequencies of the membrane-coupled Helmholtz resonator. The conditioning equation shown above in the orange box, it actually provides a unified framework for the modal analysis of the four related systems: hardware Helmholtz resonator, circular membrane, kettle drum, and the circular membrane coupled with Helmholtz resonator. In the measurement designed for the model validation, we found that the prediction accuracy of the proposed model is pretty okay, comparable, for example, to the Kinsler's classic models of circular membrane and kettle drum. So thank you for listening, and you are more than welcome to leave your feedback or comments. Thank you.